All right, so our goal today is to talk about rotational dynamics, and particularly Newton's second law for rotation. So you're actually going to do a lab really before I teach you a lot of stuff. So this is just kind of like the basics that you need to do to understand what we're talking about. So rotational equilibrium was a case in which a rotating rigid body, which could be something that can rotate, like you might expect like a wheel, or it could be a rod, or any other type object that you have. If that rotational equilibrium condition is met, that your net torque is zero, then that implied also that your angular velocity was zero, or your angular velocity was constant. So we actually did look at some cases of rotational equilibrium last semester when we did uniform circular motion, because if you had a rotating rigid object and your angular velocity was constant, it was uniform circular motion. We talked about things like centripetal force and so forth. But now we're going to talk, instead of just talking about centripetal force, we're going to talk more about like angular dynamics, talking instead of about linear speeds around circles, about angular speeds around circles. So rotational dynamics is the study of objects in which the net torque does not equal zero. So just some things to remember, that if our net torque doesn't equal zero, then that means that we have an angular acceleration. So that means that our angular acceleration does not equal zero, because that means we're going to change speeds. Our angular acceleration is defined as the change in angular velocity over the change in time. So if I was to think about what this meant for like an object moving in the circle, that if I started off maybe say here at some t equals 0 or something, then I could be moving at some linear speed. And then if I have some sort of angular acceleration, that means that I'm going to be increasing in speed, so that at some other point in time, I have some larger speed. Now, I will have some sort of angular velocity at this point, but remember that angular velocity was trickier to draw in a diagram, because technically my angular velocity points out or into the page. So like in both of these cases, my angular velocity would be out of the page because I'm moving counterclockwise. But that angular velocity is essentially going to be increasing, causing me to move faster around the circle. But that vector technically points out of the page. So when you have an angular acceleration, then you're also going to have a tangential acceleration, because your tangential acceleration is the change in tangential speed over time. So alpha and tangential acceleration are related. And we defined that tangential acceleration was always equal to r times alpha, which is our angular acceleration. Now, there is still going to be a centripetal force acting. Because if a point on a rigid object is moving in a circle and getting faster, then in order for it to change directions, there still has to be a centripetal force, so there has to be a centripetal acceleration. Now, that centripetal acceleration, no matter where it's located, always points in towards the center. The tangential acceleration would be pointing tangent at any instant in time. Your centripetal acceleration was equal to vt squared over r, which if you substituted in for angular variables would be r omega squared. So tangential acceleration, centripetal acceleration are different. You could have, if you're changing directions, your centripetal acceleration must be present. If you're changing speeds around the circle, you have to have tangential acceleration. So if you were going to be moving in a circle at all, then you were going to have to always have centripetal acceleration. Now, if you have a non-zero angular acceleration, then you also have to have tangential acceleration. So just in case you do have both, and you wanted to represent the net acceleration, you could do like the parallelogram method or something to add vectors, and I could get A, where A is going to equal, where a squared would be at squared plus ac squared, or a is the square root of at squared plus ac squared. So centripetal acceleration is responsible for changing directions in a circle. Tangential acceleration is responsible for changing speeds around the circle. The acceleration is going to be the vector sum of both the tangential and centripetal components, and your angular acceleration is related to your tangential acceleration by the radius r. So there's a lot of different types of accelerations that we're dealing with here. Now what we're going to do mostly in rotational dynamics is we're going to talk about alpha, but remember that you can always go back to linear variables using these relationships right here. So if we take a look at some of these definitions, I want to know how torque actually comes in and relates to these variables. Well, if I am going to be accelerating around the circle, then there must be some sort of force that is tangent to the circle if I am going to have a tangential acceleration. So if I'm going to change speeds around the circle, I have to have a component of the force that is tangent to the circle. Now, if I'm going in a circle, there has to be a force that is also pointing in. I have to have a centripetal force if I'm going to change directions, but now we're talking about the force that's required to actually cause the object to change speeds around the circle. So what I'm going to do is I'm going to simplify this diagram here a little bit. And I'm going to assume that I'm applying some force F tangent to the circle. So I'm applying F at some radius r, I'm going to use lowercase r. That F is tangent, so it's perpendicular here to the radius. And that force is going to cause a tangential acceleration, which is going to cause this object to change speeds. So that means that if I have a force at a radius r, I must be applying a torque. And I could do that because my radius would go here from my axis of rotation, and I could draw a vector r. And if I point my fingers the direction of r, rotate my palm the direction of F, and curl my fingers, I can see that I'm going to get a torque that actually points up out of the page. So my torque would be a vector pointing out of the page, which is causing, in this case, a counterclockwise rotation. So let's go back to our definition of tangential acceleration. I can actually define, because of Newton's second law, that acceleration is the ratio of force to mass. So if, let's say, this was like a ball on a string, then that ball would have some sort of mass here. So if I was looking at, say, that point, then I would end up with, say, that force being applied to this mass m, causing an acceleration, but that acceleration is actually going to be my tangential acceleration. So because this force is parallel to tangential acceleration, it's not responsible for changing directions. It's responsible only for changing speeds. So for example, there could be another force. There could actually be a tension force here. You know, there could be a tension force pointing in towards the center of circle that would be responsible for centripetal force, but it would not be contributing here to the changing speeds. It would just be responsible for changing directions. But like I said, we're talking a little simpler than that. We're just going to pretend like there's just this one force acting that we care about right now. There are other forces acting, but they're not affecting the tangential motion, so I don't need to worry about them. So I can sub in my definition of tangential acceleration here, which is r times alpha, to get this into angular terms. So that's F over m. I can then solve for angular acceleration. Angular acceleration is going to be F over m times r. Well, I also know that there is going to be a torque being caused by that force. And that torque is going to equal r times f, because r and f are perpendicular to each other. So that means that f is equal to torque over r. So I can sub in for this force, because I'm more interested in torques than I am interested in forces right now. And I get that alpha is equal to torque over r divided by mr. So if I rearrange, I get that alpha is equal to torque over mr squared. So what this does is this provides a relationship for me between my angular acceleration and the torque. So what this does is it tells me that my torque is related to my angular acceleration. And if I look, this tells me that torque is directly proportional to angular acceleration. That's kind of awkward. So this is the directly proportional to symbol, which actually technically should look a little more like that. It's kind of like an 8 cut off. And then this is angular acceleration. So that's alpha. So torque is directly proportional to my angular acceleration. Just like force is proportional to linear acceleration. So this is Newton's second law. This is Newton's second law for rotation. So what I can do is I can then solve for torque. Torque is going to equal mr squared times alpha. So this also shows that my torque and my angular acceleration are directly proportional. This little fun thing right here is very interesting. So when I look at Newton's second law, I know that force is mass times acceleration. So if I apply a force to a mass, I get an acceleration. The larger the mass, the smaller the resulting acceleration. Now what this is telling me is if I apply a particular force, then both the mass and r, which is the location where the force is applied, are going to affect the angular acceleration. The larger this product, the smaller the angular acceleration. So that's where that position of that length of that lever arm for the torque comes in and comes into play. Now we also called this mass, this was also called inertia, because it's mass that supplies a resistance to a force. The bigger the inertia, the smaller the acceleration from the resulting force. Well, this guy right here is also inertia, but this is rotational inertia. So it is the inertia that supplies resistance to angular acceleration. So that if you apply a torque, then depending on the amount of rotational inertia, you're going to get a larger or smaller amount of angular acceleration from that torque. Rotational inertia is one of the more difficult concepts for some people to understand in this unit. We're going to spend a lot of time talking about it tomorrow. But what we do to simplify it down is we call rotational inertia I. I for inertia. So that I can write Newton's second law for rotation as angular acceleration is equal to, well, let's do the torque version. Basically, my net torque is equal to I times alpha. In this case, this was just the torque due essentially to force F because there was only one force, but there could be multiple forces causing multiple torques. So my net torque is equal to I times alpha, where I is my rotational inertia. This is also called the moment of inertia. In chemistry, you might have talked about dipole moments. When you were talking about properties of molecules and atoms and things like that, polar molecules and so forth. So this moment of inertia is very similar to a dipole moment, but we also call it rotational inertia. But sometimes they call it moment of inertia because you don't technically have to be rotating to have a moment of inertia. So kind of interchangeable. And then, of course, this is your angular acceleration. And this is your net torque. Net torque has to be in units of Newton meters. Rotational inertia, if we look, it's a mass times a distance squared, so it's going to be kilogram meter squared. And angular acceleration is in radians per second squared. Remember, anytime you multiply radians by anything else, the radians is just a placeholder. So if I multiply radians per second squared, I get kilogram meter squared per second squared. A kilogram meter per second squared is a Newton. So therefore, a kilogram meter squared per second squared is equal to a Newton meter. So you see the units actually do work out between those. So the moment of inertia is not always equal to mr squared. Your moment of inertia is always going to equal to some constant times mr squared. So, but that constant can be any number between basically 0 and 1. And we're going to talk a lot more about this. So this mr squared thing was specific because we used a point mass. A point mass has a moment inertia of mr squared. A rotating disk would have a moment inertia of a different value. So we'll talk about that. So what you're going to do is you are actually going to determine the moment of inertia experimentally for using a pivot lab by somehow determining the angular acceleration and the net torque and kind of graphing those and using linearization techniques to find the rotational inertia of an object using the pivot lab. So that's where you're headed next.